Hello and welcome to module 5 of source coding. Let us look at the brief outline for today's lecture. We will revisit source coding theorem. We will again look at what do we mean by efficiency of a code. Then we will look at one practical prefix coding scheme called the Huffman coding scheme. And then we will explore coding in blocks, not one symbol at a time, but coding several blocks at a time. And finally, we will look at some examples. So, this is the broad outline for today's talk. We start with a quick recap of what we did in the previous lectures. We have established that whenever symbols occur with different probabilities, there is scope for compression. That is, there is a possibility to represent them more efficiently. That brought us to the notion of variable length codes, which means that symbols may have different lengths of code words attached to them. We looked at Kraft inequality and we started to scratch the surface of the source coding theorem. So, let us recap a quick example of a prefix code. We did this example in the previous class. We have the first 8 alphabet of the English language, A, B, C, D up to H, and we have a corresponding code word. So, this whole set is a code. A code is a collection of code words. And what we observed in the previous lecture is that no code word forms the prefix of any other code word. We can do a quick sanity check. For example, 00, which is a code word of A, nothing begins with a 00, or 011, which is a corresponding code word for C, none of the code words start with 011. This means no code word is a prefix of any other code word. This is the basic essence of this code. This condition that no code word forms the prefix of any other code word is called the prefix condition, right. And since these codes are such that we do not have to wait to declare the results. If we have an input bit stream coming, the moment we find a sequence of bits corresponding to any valid code word from our table, we declare the result. Then and there, we do not have to wait for it. Therefore, these codes are also called instantaneous codes. Please note that suppose we make this condition suffix codes as opposed to prefix code, then we probably cannot instantaneously declare the results. Okay, so, we have to go through several code words coming back, and then we have to walk backwards to understand what was really sent. So, prefix codes work, whereas suffix code may not work, though both are uniquely decodable. We also saw examples of codes which are not uniquely decodable, that is, you can have multiple possible answers to the bit stream that you receive. We observed in the previous class the Kraft inequality, which is shown as follows: summation k is equal to 1 through L 2 s power minus k n k less than or equal to 1, right. This is a condition for prefix condition. Let us look at the source coding theorem that we talked about. Here we have L output symbols from a source. The source has a finite entropy h of x. Now, each of the symbols x k have an associated probability p of x k. Okay. Then the source coding theorem says that it is possible to construct a code that satisfies the prefix condition and also has an average length r bar, which is limited by h of x as the lower bound and h of x plus 1 as the upper bound. The units are in bits. So, please note that r bar, which is the average length of the code provided it follows the prefix condition, is pretty efficient. The best you can do is to take it down up to h of x. But even if you can't, and sometimes it will not be in your control to make the average length of the code down up to h of x, if it is a prefix code, it will at worst be upper limited by h x plus 1. So, it is off by 1 bit, not too bad. So, it is worth exploring what R bar is when we have a prefix code. It also tells us that once we have a prefix code that satisfies R bar is equal to h of x, we should abandon further search, because we have reached the ultimate. And intuitively the source coding theorem tells us that if a source has higher entropy h of x, then on an average we require more number of bits to represent the symbols. Please note the key word is on an average. We also defined the efficiency of a code as a ratio of h of x divided by R bar. So, clearly it is less than or equal to 1. Efficiency of the code really tells us how much we can compress the source symbols, and we will use this source coding to compress data, speech, text, audio, image, X-ray data, any samples that you get from the vibrations of the bridge, any signal that you get, wherever there is redundancy, we should be able to compress it, and we must compress it, because today the storage of bits and the transmission of bits both require resources and is expensive. So, it is important that whatever can be compressed should be compressed. Since this prefix code is such a good case to argue for, we should look at an example how to come up with a prefix code. And this was introduced in 1952 by Huffman as a variable length encoding algorithm. What it requires is the source symbol probabilities Pxi. So, suppose there are L possible symbols, each one has an associated probability Pxi. Now, this Huffman coding is optimal in the sense that the average number of bits required to represent the source symbol is a minimum. We can't do any better than this on an average, and it also meets the prefix condition. So, let us look at it. How do we do Huffman coding? The first thing is that you collect all the source symbol probabilities and arrange them in a decreasing order. So, in this example, let us have 1, 2, 3, 4 up to n probabilities. Of course, we are not showing P1, P2, P3, but right at the bottom we have Pn as the lowest probability, Pn minus 1, little higher, Pn minus 2, higher than that, and so on and so forth. So, we always start with the bottom of the ladder. So, on this ladder we have arranged all the probabilities of occurrences of the symbols, but bottom is the smallest and top is the highest. So, we focus our attention on the bottom of the ladder. So, what we do is take the bottom two, and we will explain the rationale behind it, but first idea is to take the bottom two and combine them. How do you combine them? You tie them up together and add their probabilities. So, in essence we are making one complex signal from the bottom two symbols which are least probable. Okay. And then once we add them, we write the net probabilities, because probabilities will add up. Now, what we do is we repeat this step for two symbols at a time as we go along. For example, now Pn and n minus 1 together have formed one complex signal that becomes the lowermost, provided Pn minus 1 plus Pn, the sum of the probabilities is still lower than Pn minus 2. Otherwise, you have to rearrange this complex symbol along the ladder and place it at a level where it is again in the decreasing order. So, each time we perform the combination of two symbols, obviously we reduce the total number of the symbol by 1. So, at every step we lose one symbol, and as we go along we will end up finally with one symbol, and that symbol has probabilities of all the symbols added up, and it should add up to 1 because the probabilities must add up to 1. So, here we have taken the bottom two symbol, labeled them as a complex symbol. It is still lower than p n minus 2. So, it occupies a lower level, and then we combine p n minus 2, the probability, with this probability to give another combined symbol. So, after 2 steps, out of these 3 possible symbols we are only left with 1. At every step we lose one symbol. And now we write the combined probability here. Let us look at an example. Suppose there is a discrete memory-less source with only 7 possible symbols xi 1 through 7, and we have the corresponding probabilities. So, in this table we write the probabilities. Just for reference, suppose these probabilities were all equal. Suppose the symbols were equiprobable, then in order to represent 7 or even 8 symbols, we would clearly require 3 bits per symbol. Right. Log to the base 2 8 will give me 3. So, 3 symbols, 3 bits are sufficient to represent the symbols, but can we do better? That is the question. And here we have the probabilities. So, first step is we have arranged them in a decreasing order, x 1 most probable, x 7 least probable. Now, here is the arrangement in the decreasing order. We start with the bottom two, 0.01 and 0.02, I combine them up, and I am glad to see that 0.03 is still less than 0.04. So, my decreasing order is 0.37, 0.33 going up to 0.04 and then 0.03. So, I still have now instead of 7 we have effectively 6 symbols with their probabilities right here. Okay. Now, we continue this process, we combine now this 0.03 with 0.04, it will add up to 7, and then 0.07 combined with 7 and so on and so forth. So, I keep adding them up and I form this structure. Okay. So, please note 0.01 plus 0.02 is 0.03, 0.03 plus 0.04 bottom 2 0.07, 0.07, 0.07, big question, which is bigger? Well, we can toss a coin to choose which one is bigger. Right now let us say this 0.07 is lower than this, but nothing stops me from putting this symbol higher up than this. We will look at a subsequent example to prove this. So, 0.07 plus 0.07, 0.14, still lower than 0.16. So, the probabilities at this stage is 0.37, 0.33, 0.16 and 0.14. Okay, great. We combine bottom two, 0.30, probabilities are 0.37, 0.33, 0.30, still in the decreasing order. I have got deeper into the tree and so on and so forth. I keep combining 0.66 and so on and so forth. We can take it up to 1. We can flip this also, but we are at the last stage. So, 1 means I have added all of them correctly. Now, suppose having constructed this Huffman coding tree, I am curious to find out what should be all the code words associated with x 1 to x 7. Let us choose x 4 for example. All we have to do is follow this tree backwards. So, this is the mother node and we go up to x 4 by following it up. So, I go here, I have a choice, I go up or go down. I need to go to x 4. So, I go down. The moment I go down, I add 1. So, So, whenever I have to take a choice, go up I will add a 0, go down I add up a 1. Therefore, these are labeled 0 1, 0 1, 0 1 and so on and so forth. Since my target symbol is x4, 1 and I go down 1 and I need to go down 1, but now to go to x4 I go up and I get 0. So, I add 1, 1, 1 and 0, and that should be my symbol, the code word for x4 and so on and so forth. So, what is unique, what is interesting is as follows. Please note, the higher the probability, the fewer bifurcations it has to go through. So, this particular guy x1 most probable had to just go through one bifurcation. So, it just gets the number 0, but this guy probably had to go to 1, 2, 3 bifurcations. So, as we go down the ladder, we will have to carry on through more steps, and consequently I will have a larger representation for less probable symbols, right. Now, I have got these probabilities. So, it is very easy for me to calculate the h of x. Again, I can have corresponding code words. So, it is very easy for me to multiply the length of the code word with the probability of occurrence and average it out to find out the average code word length. So, invariably I will calculate h of x, plug in the values, I get some numbers. So, answer is 2.152 bits and I get the r bar average code word length as 2.17 bits. It is not surprising to see that r bar is greater than the h of x. H of x is the holy grail, the best we can do, and I can take the ratio and I can give you the efficiency of the code. So, here is a detailed calculation how I received h of x and r bar. H of x is nothing but summation over all symbols 7 p x k log to the base 2 p x k. If you solve this, you get this value, and similarly for the average code word length of the code word into probability of occurrence. So, this one is 1 bit long and 0.37. So, I multiplied 1, the second one is 2 bit long multiplied by 0.33 and so on and so forth. So, I get 2.17 bits and efficiency is 0.97. Now, let us look at it a little bit more carefully. What have we done so far? We had these nice symbols x1 through x7 and they are arranged in the decreasing order of their probability, and we have been able to find the code words associated with them. Categorically for x4 we had found 1 1 1 0. Similarly, we find for all others. But what we have added is this table for self information. Clearly, x1 which is more probable has a less self information as compared to x7 which is very rare. Remember, self information inversely proportional to the probability of occurrence. So, clearly the self information which necessarily does not have to be an integer are all over the place, right from 1.43 right up to 6.64. Code words on the other hand must be integers, right. So, we cannot really fine tune too much in terms of the code word lengths as opposed to self information. Where does the compression come from? Well, if the information is less, I should use fewer bits, because units of information is also bits. So, in principle I should actually use 1.43 bits to represent this first symbol, but I am using 1 bit. I should use 1.599 bits to represent the second symbol, but I am using 2 bits. Wasteful, but I have no choice. Either I use 1 bit to represent or 2 bits to represent, and so on and so forth. This is my dilemma. 2.64. This symbol x3 only commands information worth 2.64 bits. but unfortunately Huffman has allocated 3 bits, wasteful, and I will be paying in terms of my poor R bar and hence the poorer efficiency of the code. Where are we losing the efficiency? It is all here. I just do not have a choice. Look at x6, it requires 5.64 bits to represent it, and I have got 1, 2, 3, 4, 5, 6, overestimated. But all is not bad, x7 requires 6.64 bits, but again I have got only 6 bits. So, win some, lose some, but on an average I am a little off than my h of x. H of x is completely determined by the self information. Average self information is h of x. Okay. So, this is the first weakness of Huffman code. Let us look at another example. Okay. Again we have our 7 symbols. Please note, if we had equiprobable, then we would have no choice but to represent 3 bits per symbol. Please note here, in the previous example we were able to reach up to 2.17 bits instead of the worst case analysis of 3 bits per symbol. But in this example, let us see what we have. Again we have probabilities, and I have taken the liberty to arrange them in decreasing order of probability. Okay. The construction of the Huffman tree is pretty mechanical. Decreasing order of probabilities, take the bottom 2, combine. So, 0.01 plus 0.02 combine to get 0.03, 0.03 plus 0.03, 0.06. But what is going on? 0.03 and 0.03, they are the same. Nobody is holier than the other one. There is no reason why this symbol should be lower than this. But for the time being, let us keep them like this, but we should be able to switch them also. But what is this? 0.03, 0.03 add up to 0.06. I have to compare again because they have to be in decreasing order of probability. So, there is no reason why this 0.06 should be lower than 0.06 here, but we have no choice. So, let us keep it here, but we could have tossed a coin and put this symbol higher up than this. But today is not my day. 0.12 and 0.12 again they are equal. Maybe I should exchange them in terms of ordering. So, the decreasing order probability ladder says 0.46, 0.30, 0.12, 0.12, but this 0.12 can be higher up than this 0.12, and then we have 0.24 and so on and so forth. So, if you do this and again calculate the h of x, it comes out to be 1.9781 bits, and R bar as expected is larger than h of x, is equal to 1.99 bits for this different example. So, please note 7 bits in this example, I changed the probabilities, but my R bar and h of x both have changed. It is obvious, if I change probabilities, h of x will change and R bar will also change. Now, we change our thinking and we say, look, this 0.03 should be rated higher than this 0.03. This 0.06 should be above this 0.06. So, what if we change the probabilities? What if we change the ordering? So, same probabilities 0.46, 0.30, 0.12, you can check with the previous example, but this time when I get 0.01 plus 0.02 as 0.03, I put this above what? This P. So, this one goes down. Please note, it will change the code word, because whether you take the upper branch or lower branch will decide whether you add a 0 or a 1. 0.06, again 0.06. I say this guy is higher up than this guy, so again I interchange. 0.12, again I play the same trick, this 0.12 goes up, this 0.12 comes down. So, see how convoluted this second case is as opposed to the previous case, where each one time when I had an option, I have really twisted the arms each time of the Huffman tree, and so on. So, I add up to 1. So, I am sure that my addition is correct. So, I have taken this 0.03 and switched it over. Now, what do we find? Well, we can again calculate h of x. It goes without saying that h of x is the same as previous one, because I have not touched the input probabilities. H of x only depends on the input probabilities. So, it is the same. But what about r bar? Well, r bar is also same. So, the average code word length has not changed. The code words would have changed for sure. Have they? Why do not we look at it? So, this table tells us the two different realizations of the Huffman tree for the same set of input probabilities. Okay. So, what are those? So, we have x 1 through x 7, and you can verify that the probabilities are the same, and needless to say the self information must also be the same, right. But in the first case we did not reorder the equal probabilities, whereas in the second case we reordered them. So, we ended up with different sets of code words. Okay. So, here the third one, x 3 was 0 1 0, here x 3 is 0 1 1, x 4 is 0 1 1 0, here 0 1 0 1, and so on and so forth. The bottom one, the least probable, is 0 1 1 1 1 1 1 1, and here it is 0 1 0 0 0 1. Now, what is to be noted is, since it is based on a binary tree, the prefix condition will always be satisfied. So, you can verify that no code word either in case 1 or in case 2 is a prefix of any other code word. And finally, we write the code word length. So, code word lengths are also the same. So, clearly when I find r bar, I multiply 1 into 0.46 plus 2 into 0.30 into plus 3 into 0.12 and so on and so forth, 6 into 0.01, add them up, I get the same answer as this. But mind you, this always does not have to be. I could have done additional jugglery in between by choosing not to have all of them switched. I could have flipped the first one and flipped the third one, but not flipped this one, and I will get another set of code words, and they may not be of equal lengths correspondingly. Still the r bar magically will come out to be the same. So, in this both the cases h f x and r bar are the same. Okay. So, if you look at the efficiency of the code, you can divide the h of x by r bar to get 0.9940. Okay. So, both the codes are equally efficient, but it tells us that Huffman codes are not unique for a given set of probabilities. Okay. You can have more than one realization, but efficiency is the same. Okay. So, that is the take home message, that we can have multiple realizations of the Huffman code for the same input probabilities. So, let us explore a little bit deeper and look at another example. Again, our discrete memoryless source is generating possibly 7 different kinds of outputs, x 1 1 up to 7, and then these probabilities are associated with these symbols. So, x 1 has probability 1 by 2, x 2 1 by 4, x 3 1 by 8, appears to be a pattern 2 raised to the power minus 1, 2 raised to the power minus 2, 2 raised to the power minus 3 up to 2 raised to the power minus 6, but this one, last one, I need all the probabilities to add up to 1. So, it is again 2 2 raised to the minus 6. So, how does it work? Add these two up, you get 2 raised to the minus 5, add these two up, you get 2 raised to the minus 4, 2 raised to the minus 3, keep adding and you will add up to 1. So, the probabilities add up to 1, it is a valid probability measure. But having put this probability in this funny manner, we note another very interesting thing. We find that the self information are all integers, log to the base 1 over p xi. So, here it is 1, 2 right up to 6. Suppose we do Huffman coding on it, we get this following prefix code. Now, we write the corresponding code word length side by side. What we observe is very interesting. Finally, the code word length, which has to be an integer, is the same as the self information, which is by design an integer. We have been able to finally map the length to the self information length 1 to 1. So, x 4 has the self information 4 and we have done justice to it, we have only allocated 4 bits. The rare event x 7 has self information 6 bits and I have given it 6 bits. So, we have really done allocation optimally. Bits are resources. We have not over allocated or under allocated. We have matched it. So, what it means is this very unique distribution only allows us to do this. And this should not be a surprise. If you calculate the h of x, it is 1.9688 bits, and if you calculate the average code word length, it is also 1.9688 bits. So, we clearly have the efficiency equal to 1. We have reached the rock bottom, the best we can do. This special probability distribution and only this special probability distribution allows me to reach r bar equal to the lower bound h of x. And this also tells you why in all other cases my r bar will be greater than h of x, because I just can't match the self information with the integer code word length. Fine. So, this probability distribution is called d-adic. So, the distribution probabilities are d raised to the power minus n for some integer n. The Huffman coding scheme has been able to match the code word lengths exactly to the probabilities and hence the self information of the symbol. Okay. And therefore, we have been able to achieve eta equal to 1, the efficiency equal to 1. But this kind of a nice beautiful distribution is not always found in the real world. Okay. So, this is where we are. So, let us look at the Huffman coding from a slightly different perspective. Let us look at a person whose job is to allocate bits, all right. So, every time he reaches a bifurcation, this person has to traverse a path from this base up to one of the valid symbols and allocate the code words. Okay. Let us look at even a simpler example. So, what we are trying to do is try to help this person allocate a code word to a particular symbol, and the way he does it is he either takes the upper path or the lower path. But to take a path, to take a decision, he uses a bit. Okay? So, the value of the decision is 1 bit. Which path to choose? The upper path or the lower path? Whenever you have to take a decision, you have to invest in bits. But the problem with this guy is whether the decision is easy or the decision is difficult, he has to allocate one bit each time. Okay? What do you mean by decision is easy? Well, if the probabilities are 0.9 and 0.1, right, it is an easy decision. But if it is 0.5 and 0.5, it is a difficult decision. So, that difficult decision warrants one bit, but an easy decision does not require it to waste one bit for each one. And that is the reason why the resource allocation while going up to the end is not optimal. Only when the bifurcation is equiprobable, say 0.6 and 0.6, then it is worth allocating one bit for this decision. But if I am mapping 0.46 and 0.50, they are not equiprobable. Each one does not deserve one bit. Or if I am doing some other 0.24 and 0.3 adding up to 0.54, again they do not each reserve one bit. Why am I saying this? Tomorrow if we have to improve upon this method, we should be able to allocate fractional or proportionate amount of bits when we go up or down. Then we can do better than this. And we will come to a method which allows us to allocate bits on the real line. But right now we are stuck with allocating either a 1 or a 0 when we go up or down the stream. Okay. Now let us look at a slightly different approach. We ask ourselves the question, why do we work only symbol wise? What if we combine two or more symbols together? Okay. So, well, suppose we have a bit stream and we do not work symbol by symbol, but by blocks of symbol. All right. But since they are independent, if the source has an entropy of h of x, the blocks of B symbol would have an entropy B h of x. And if we apply source coding theorem, because we treat this combined blocks as the super symbols, then we will have a corresponding R B, and it is upper bounded by B h of x plus 1. So, let me explain. Suppose we have a bit stream and we choose to take 3 bits at a time. And declare them symbols x1, x2, x3. Well, these themselves have their own probabilities px1, px2, px3 and so on and so forth. In fact, if you look at this example, you have right from 0, 0, 0, 0, 0, 1, 0, 1, 0 up to 1, 1, 1, you have got corresponding probabilities px1, px2 and so on and so forth up to px8. What it means is that I can now do Huffman coding at these complex symbol levels. Let us look at the equivalent source coding realization for that. So, we now have, instead of h of x, we now have b h of x, and R b is the average number of bits per block. Okay. This happens to be my b. So, R b bar is the average number of bits per b symbol block. So, we can divide all the sides by b and we can rewrite the bound as h of x less than or equal to r b bar over b less than or equal to h x plus 1 over b. But r b bar is the average number of bits required to represent b symbol block. But how many symbols does it have? B symbols. So, r b bar divided by b is the average number of bits per symbol, right, and that is my r bar. So, again we can compare apples with apples and I am left with h of x less than or equal to just r bar less than h of x plus 1 by b. So, working blockwise has been able to pinch, squeeze the upper bound. Earlier it was h x plus 1, now it is 1 over b, and as I make the block size b larger, I try to squeeze the upper bound, and the upper bound squeezes and it tends to h of x. So, Huffman coding in blocks would be able to give me a much higher efficiency. Let us look at an example. This time let us have 3 symbols only with probabilities 0.4, 0.35, 0.25, and mechanically I find my self information for these 3 and I do a Huffman coding and I get 1 0 0 0 1 as my 3 code words. Very simple. H of x is 1.55 and average code word length is 1.6 bits. So, clearly efficiency is less than 1, but how much is it? It is 0.9743. Fair enough, 3 bits, given probabilities, all the steps are mechanical, this is the best I can do. But I now wonder, can I work block by block? Theory says that I can do better, why do not we give it a try? So, what are my pairs? I make b equal to 2. So, I pair up each one and I first find out the probabilities, all right. So, what does it mean? I have x1 x1, x1 x2, x2 x1, so on and so forth up to x3 x3. So, 9. Independent probabilities multiply. So, x1 was 0.4, so x1 x2 x1 x1 is 0.16, right. x3 is 0.25, so x3 x3 is 0.0625. And now I found the self information and I do a Huffman coding on it. This is pretty mechanical, but this time I find that if I do your h of x, so we find for the symbol which is 2 h of x is 3.1177 bits, consequently h of x is 1.5589, and for a block of 2 symbols 2 r bar is 3.175 bits and r bar, that is per symbol, is 1.588. How does it compare with the previous one, where this time our efficiency is 0.9812, but what was it last time? Well, last time it was 0.9743. So, I have been able to squeeze a little bit more efficiency, it is better than my previous case. So, coding in blocks helps. I will not stop here, I can go beyond, I can go to x1, 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 x2 right up to x3, 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 and I get the probability corresponding probability distribution, and I can write the self information and code word and find it is better. Why is it working better? The answer is pretty simple. If you look at here, the self information is very coarse because the probabilities are very coarse. There are 3 symbols, 3 probabilities, they must add up to 1. Whatever I have written the self information. I am trying to match the code word length to the best. So, 1.3 is mapped to 1 length, 1.5 is mapped to 2 and 2 is mapped to 2. So, I have only done justice to x3 in terms of allocation of the number of bits to the self information value. Rest all I have not done a good job. But if you look at this two symbol pairs, right, the number of elements now has gone up in my combined symbol list. It is now 9, but probabilities must add up to 1. So, the granularity, it has become much more fine, the distribution has become much more distributed. So, the self information values, as you can see, are not such discrete, it is slightly easier to map them up. So, 2.8 is now mapped to 3 as opposed to 1.5 being mapped to 2. What a poor map. So, we are trying to understand why this grouping works. Mathematically it works, but we are trying to understand why it works. So, if you can see again 2.83 is trying to map to 3, not a correct map, but a closer map. 3.02 map to 3, yeah, I am doing a better job, right, and so forth. And somewhere of course, it is not so good. So, 3.5 is mapped to 4, not so good, and therefore, I pay and my efficiency is farther away from 1. This 4 is mapped to 4. So, we have done a good job in the end. Okay. So, the bottom line is, if you combine, if you work in groups, you have a chance of improving your efficiency. Price is the computational complexity goes up. You can see the size of the Huffman tree will increase exponentially, and that itself will cause additional problems at the cost of giving you a better efficiency. Okay. So, we now come to the end of this talk. Let me summarize what we have done. We revisited source coding theorem. We talked about the efficiency of a code, very important, closely linked to the compression. Then we looked at Huffman coding. We finally looked at an example why coding in blocks helps, and we of course looked at several examples throughout today's lecture. What if conditions, what if you interchange probabilities, equal probabilities, what if you distort the Huffman tree, twist the branches and things like that, and we got some insight into why Huffman tree works and why it does not work beyond a certain limit, and probably how you can make it work even more efficiently. So, we come to the end of this module.